Hi, my name is Julia Silge, and I am a data scientist and software engineer at our studio. And today we are both celebrating Black History Month by learning about the Tuskegee Airmen, Black pilots who flew in World War II, and we're learning about a package I haven't talked about before, which is the infer package. So the infer package is a tidy models package for a statistical inference, and let's use it to learn more about the Tuskegee Airmen and understand the relationship between things like what kind of aircraft they flew and their ranks.
All right, let's get started with some statistical inference for the Tuskegee Airmen. Um, I have always loved learning about this part of our history, such like a cool story. Today, we're not delving so much into the stories of these members of our armed forces, but instead are going to do some statistical inference on some of these relationships. So. We can look here. I'll pop it up here into the viewer so we can see what data we have about them from Tidy Tuesday this week. We have information like when, names, when they graduated, what their rank was from graduation, and then this about, were they at the Air Force Base in Tuskegee or were they elsewhere? Most of them were from there, and what class they were part of, the pilot type. So this is about what kind of aircraft these pilots piloted, and then information on where they were from, um, victories, and whether these folks were lost. And I mean, that's part of the stories I always heard growing up about this group of group of folks is like how successful they were, which is really cool to have this data on. We let's I think we're going to focus on two things here. I think are um, which are lots of this is interesting, but these two will be a good fit for what I want to try to do today. The first is looking at this pilot type. You can see, there's many more of single engine pilots than the other kind, and we've got this misspelling here. So let's fix that first. So let's say airman raw, and it's only in one place, but often if I have this kind of uh, misspelling type things, one way that I will do is we'll just replace misspellings with correct spelling. So we want to replace the misspelling. Oops. I need to say in what string I am replacing them. And then what do I want to replace it with? I want to replace it with the correctly spelled word, like this. So now if I do this and I count pilot type, now that it's spelled correctly. Okay, so let's save this. I don't think I'm going to need to do any other data cleaning up here. So let's go straight and let's look at the other thing which I'm interested in here, which is so let's put pilot type on the x-axis. And the other thing I'm interested in is that rank at graduation, because I'm, interested in whether there are any differences. Like, do people who graduated a different rank, did they always get sent to one kind of plane or not? So let's use genome bar with stat equals count. And what this will do is it'll make us a bar chart of these. It'll count it up for us. And here we go. So let's make this much bigger so we can see it. So we can see again here, single engine, many more of them here. The next is twin engine. Very few people got sent to being a service pilot, and this liaison pilot is in the middle. Let's look at the breakdown here. So many of these airmen graduated as second lieutenants. I went to look at some of the history of, um, airmen during World War II. And so flight officer, it turns out, is a rank that is that is lower than lieutenant. So a lieutenant is a higher rank than a flight officer, and I believe it's not a rank that's used anymore in the Air Force, but it was at the time. So we've got, and first lieutenant is a higher rank, so it goes, and then captain is even higher than that. So it's tiny, tiny numbers of people who graduated with as captains. Um, a very small number who graduated as first lieutenants, many as second lieutenants, and then the flight officer is less again. Let's look at the breakdown here. So it looks like if you were a first, like there's more first lieutenants over here proportionally, maybe even by number, in the liaison pilots, and over here we see this sort of difference, right? Like there are more flight officers in single engine than twin engine, but proportionally, it looks like there's more second lieutenants in single engine than twin engine. So whereas it's almost close to equal in the twin engine. So this sort of difference is what I want to look at, and we can look at it with our eyes here and see it's really different, right? Like we see that those proportions are quite different. But let's use some tools for statistical inference, some tidyverse, tidy models tool for statistical inference to confirm that yes, that is a real difference, and then that we have evidence that it's a real difference, and then also to estimate how much of a difference it is. Like how different are the aircraft roles that people were assigned to based on their rank at graduation. So we are going to use the infer package. So infer is a package that is part of tidy models. So if you have installed tidy models, you have it. And infer provides an expressive grammar for a statistical inference. So like if you are going to do hypothesis testing, if you're going to do a chi-squared test, that's the kind of thing that infer is good for. So let's take this. Let us filter. I'm going to filter pilot type. You know what? Let's define these up here. Okay, so let's call that aircraft. And it was single engine, twin engine, single engine, like that. And then let us do the same thing for the ranks. And so it was. Let's look at it again. So flight off, whoops, I gotta be over here. Flight officer and second lieutenant, like that. So let's filter here. Rank at graduation is in ranks. There we go. Okay, and so we cut that down on we no longer have in our data set the airmen who flew different kinds of planes or had different ranks at graduation. So this is how many we have now. So let us yep, that all looks right. So now we're going to do our first bit of infer, and we are going to use the first verb, which is specify. So infer has a handful of important verbs that you use for the kind of analysis you want to do. So we are going to specify the question that we're interested in. So you pipe in your data, and then the next thing is a formula. So our formula is going to be pilot type x, which is the response, and our explanatory variable here is rank at graduation, like this. And I think we need to say what is a success, because we're going to do some of those kinds of statistics. And so let's say success is a twin engine, like that. And so let's call this pilot versus rank. So what we're doing here is specifying the kind of analysis that we're going to do. So this tells us, now it's the data, right? But now this object knows what is the response and what's the explanatory variable here. So now that we have this, we can start getting ready to do different kinds of analysis. We can do analysis just on on this, which is the real data that we have, but also we can create resampled data sets for us to be able to do hypothesis testing, for us to be able to estimate confidence intervals and all those kinds of things. So I'm going to set a seed. And let's take that pilot versus rank and let's pipe it to generate. And so generate, you say, is how we make these resampled data sets. So the version in the infer framework. So we're going to say how many reps we want. Let's do 1,000. And then let's say what kind of type we want. So there's several types available in infer. We can do bootstrap, permutations, or draws, which is for a theoretical distribution, which I don't think I'll do that today. So let's make bootstrap resamples like this, and let's call this bootstrapped like that. And so what this does, so remember we had about 4 or 650 before. Now we have 10 or 1,000 times that. So we've got 1,000 replicates that are draws from that that data that we have initially. There we go. So let's do the same thing now, except instead of with bootstraps, let's make a permuted data set. So instead of drawing, like from the data that we have, permuted. Let's permute the variables. And so what this will do is it will instead of drawing from the examples we have, it's actually going to shuffle the columns so that we basically can break the permute type. What did I do wrong here? I've got to hypothesize. Okay, so I'm going to hypothesize that my null hypothesis here is independence. So it's like, how are you gonna how do you want me to permute it? I had to tell it how to permute it. So I'm going to say hypothesize here that they are they're not related to each other. That pilot type and rank graduation are not related. So given the data that I have, if they were not related, give me 1,000 versions of that data set there. So I specified what problem am I trying to solve, and now I created these resampled data sets here, and now I can do all kinds of different things. Let's start with the chi-squared statistic. So the chi-squared it is a statistic, something that you can measure about numbers, like things that are in a contingency table, that like what we have here. So the chi-squared statistic is a number that tells us how much difference there is between the observed counts we have in our table. Like if I took our pilot v rank and I counted pilot type, and rank at graduation. If I counted these and then did like spread or something, we would have this table of like how many there are in these different groups. The chi-squared statistic says how much difference is there between our observed counts and the counts we would expect if there was no relationship. So wait, why don't I have flight officer? What happened? Flight officer ranks. What happened to the flight officers? Okay, I did something wrong. Let's see. What is it called? This will not work so well if I. Nope. Rank at graduation. It's capitalized. Okay. Okay, there we go. All right. And so if I do the counts, count, like that. There. And so if I, used pivot wider to make this into a little table that had pilot type and rank at graduation on like X and Y, we would have these entries in the contingency table. And so what a chi-square statistic measures is how much difference is there between what we have here and what we would expect if there was no population. So the way that we do this in infer is so remember, this is us specifying what it is that we are analyzing, and then we pipe that we can pipe it to several things. So first, let's see what is the chi-square statistic in our real data. So we're going to calculate a stat. We can do mean, median, and so forth. We're gonna calculate that chi-squared. And I think we have to, is that enough? No. We have to give it an order. So let's do the same order that we already took care of there. Ranks. So this is, let's call this observed. I think we might need it later. This is the chi-squared statistic that we have observed in this real data set of the Tuskegee Airmen. That looks big, right? But how do we know how big it is? Like, does it mean like, oh yeah, that's a big chi-square, there's a big difference? The way that we can understand how meaningful this number is, how important it is by looking at those other resampled data sets that we made. So let's take the bootstrapped data set and let's do the same thing. We will do exactly the same thing here. So this gives us a chi-squared statistic for each one of the resamples. So now I have 1,000 values of the chi-squared statistic. So let's save that as airmen chi-squared, like that. And then we can do things like get a confidence interval for this. So now we can say, I think this is like the 95% bootstrap confidence interval. We can look at the documentation to be sure. So this is the lower and the upper. So this is what we measured in our data, and this is the lower and upper confidence interval from our bootstraps resampling of our data. So this gives us an understanding of like how much this varies depending on exactly like which of these observations the airmen are in our data set. So we can not only look at these numbers, but we can visualize it. So we visualize the thing where we calculated this, and so it gives us a distribution like that. And we can also add on the confidence intervals. So I think we have to put, I'll just do this again like that. And so that is where the confidence intervals are on this. You can change these two because it's all ggplot2. So I think I used midnight blue, so that changes the fill. We can change the color like that. Maybe it'll be more clear if we make it a dashed line like that. Whoops. There we go. So this is the simulation-based bootstrap distribution of the chi-squared statistic when we are looking at the aircraft that the Tuskegee Airmen piloted compared to their rank at graduation. So I would look at this and I would say, yep, the chi-squared, like the us doing this bootstrap chi-squared tells us that yes, there is a difference. Like this does not look unrelated, but rather this looks like they're related. So now I will admit to you here on YouTube that I don't actually have a lot of intuition around the chi-squared statistic. I'm like, okay, that's a number. What does that mean? But I feel like the odds ratio does. Like I do understand the odds ratio here. And so we can do the thing with infer, you can just do exactly the same thing again. You keep your bootstraps, but instead of calculating a chi-squareds, we can calculate an odds ratio. And so an odds ratio is something that I feel like I know what that means. It is, like this many times more likely it happened in this case than this case. And so we can compute it. We can do the same thing where we visualize it like this. And so this is the distribution of the odds ratio for uh, the Tuskegee Airmen's rank by aircraft type. So it's the odds ratio of a twin engine versus a single engine for flight officers compared to second lieutenants. So flight officers are, 2 to 3, 3.5 more likely times more likely to pilot a how did I say this? Flight officers are 2 to 3 times more likely to pilot a twin engine than a single engine compared to the second lieutenants. And this is also this is now a ggplot object, so we can just use everything we're used to here. Like I'll say something like bootstrap distribution of Tuskegee Airmen's rank by aircraft type, like that. Let's see if I can. There you go. And like I can explain what this is: odds ratio of twin versus single engine, and it's for flight officers compared to second lieutenants, like that. There we go. Okay, so if we were on this problem, we were using basically a factor variable compared to a factor variable. Like notice that it tells us that when we look at this, when we specified. But you are probably not surprised to learn that you can put numeric values here, in which case you can do things like looking at difference in means. There's means, difference in means, all this kind of thing. There's all kinds of different stats. And so what infer gets you is this ability to have an expressive grammar where you say, do you want to do bootstrap? Do you want to permute things? What stats do you want to compare? And it helps, I think it really helps understand how all these statistics work. And they're not really these like separate things that you call different functions for this and this, but to really understand how related all these ideas are.
All right, so we were able to, confirm this difference in these subgroups in the Tuskegee Airmen, and we were also able to estimate the odds ratio of how different were these ranks at graduation in terms of the aircraft that they flew. So the authors of the infer package, I believe, were originally thinking about a teaching application when they built this, and I think you can see how great that would be as a way to learn about statistical inference, statistical tests, and so forth. But also I just really love this expressive grammar that it has, how flexible it is, and so we can see that it's very applicable to real world work as well. So I hope this was helpful, and I'll see you next time.